Okay, problem 19. So this question is about the Smith number in number theory. A number is called a Smith number if it's a composite number for which the sum of the digits is equal to the sum of the digits in its prime factorization. We want to find the sum of all possible prime numbers such that, first of all, it's less than 100, and second, 12 times that prime number should be a Smith number. So first of all, it's easy to check that P cannot be 2 or 3. Well, we can just check whether 12 times 2 or 12 times 3, whether that's a Smith number or not. So yeah, they're not Smith numbers. So P cannot be equal to 2 or 3. Now we know that this 12P, well, the prime factorization of 12 times P is simply 2 times 2 times 3 times P. Okay, so let's use Sn to denote the sum of digits of number n. Then since 12P is a Smith number, we know that S of 12P should be equal to 2 plus 2 plus 3 plus S of P. All right, so basically we want to find a prime number P that is less than 100 such that this is true. All right, so here's the trick. So basically, whenever you see the sum of digits in a question, then the first thing you should think about is to consider its remainder mod 9. So let's do that. S of 12P, that is congruent to 12P mod 9. So here we're using the property that the sum of digits of the number n is congruent to the number n itself when we do this mod 9. And on the right-hand side, we have this 2 plus 2 plus 3 plus SP. That is congruent to 7 plus P mod 9. Okay, so we have, since the left-hand side of these two linear congruence equations, they're equivalent from our condition. So that means 12P is congruent to 7 plus P mod 9. Cool. So we know that 11P is congruent to 7 mod 9. Then we need to solve this linear congruence equation for P. So since we're doing this mod 9, so you don't need to try many numbers, right? At most you need to try 9 numbers. So you just try if P is congruent to 0 mod 9, that doesn't work. You can try 1, you can try 2, you can try 3. So it turns out that P should be congruent to 8 mod 9. Okay, so now we need to find all of the prime numbers under 100 that is congruent to 8 mod 9. So I guess the easiest way to do that is to just list out all of the numbers under 100 that are congruent to 8 mod 9. So let's do that. We start with 8, but of course 8 is even number, it's not a prime. So we can start with 17. And then we need to add 9. We got 26, but I guess we can skip all of the even numbers there. So we can just directly add 18. So we have 35 here, and then 53, and then 71, and then 99. Of course, 35 is not a prime number, 99 is not a prime number. So we're left with 3 candidates, 17, 53, and 71. We need to check whether our requirement is satisfied with p equal to those numbers. So basically, we need to check the sum of digits of 12 times p, whether that's equal to 2 plus 2 plus 3 plus the sum of digits of p. So for 17, 12 times 17, that's 204. And the sum of digits there is only 6. And the right-hand side is of course 7 plus s of p, which is clearly greater than 6. So 17 does not work there. Then we need to try 53. So 12 times 53, that's 636. And we take the sum of digits. So it's the sum of digits of 636. And that's 15. Now we also need to do this 2 plus 2 plus 3 plus s of 53. So that's 7 plus 8, which is also 15. Right, so seems that 53 works there. And finally, we need to check the 71. So s of 12 times 71, that's s of 852. That's also 15. And then 2 plus 2 plus 3 plus s of 71, that's 7 plus 8, which is also 15. So 71 also works here. So we found two numbers, 53 and 71, both of them work. And I guess we need to take the sum. So that's 53 plus 71, that's 124. Cool, so the answer is D. Problem 20. So the key point to this question is to find the distance from O2 to the axis of this frustum. So let's draw the axis here. And then we draw the perpendicular line from O2 to the axis. And let's say O2P is perpendicular to the axis here. So first of all, we have O1, O2. Since the two spheres are externally tangent to each other, so the distance between their centers is simply the sum of the two radius. So O1, O2 is equal to 3 plus 7, and that's equal to 10. All right, so I want to find the length of O2P. We know O1, O2 is 10, so only need to know the length of PO1. So we know the height of this frustum is 18. we also know that the distance from the point P to the top face there is equal to the radius of the small circle. So let's say the point here is A and the point here is B. So PA is equal to the radius of the small circle, so that's 3. We also know that O1B is equal to the radius of the larger circle, so that's equal to 7. Then we know this PO1 is equal to 18 minus PA minus O1B, so that is equal to 18 minus 3 minus 10, minus 7, which is equal to 8. Now we have the Pythagorean theorem. So PO2, that's equal to square root of O1, O2 squared minus PO1 squared, which is equal to square root of 10 squared minus 8 squared, and that's equal to 6. Okay, so let's see. We know that the distance from O2 to P is equal to 6. And if we want to have more spheres inside the frustum, then the distance of the center of the new sphere should also be should also have the distance 6 from the point P. So let's draw a circle around point P with radius 6. So center is P and the radius 6. Now, if we look at the plane that is parallel to the top and the bottom, and also through the point P, then we see that if we just cut everything using such a plane, then the small sphere here is going to be a circle. So the center of the circle is O2. And the radius of the circle is just the radius of the sphere. So that's equal to 3. Okay, that's our O2. And now the question is, how many circles can we draw with centers on the circle P and also the radius equal to 3, and the circles cannot overlap. So it seems that we can simply choose the 6 points on the circle that form that are the 6 vertices of a regular hexagon. So we have another point here. Let's say this is x1, and then x2, x3, x4, and x5. So those 6 points there, they are 6 vertices of a regular hexagon. And we know that the distance between 2 adjacent points is just all equal to 6. So that means if we draw a circle around each of those points with radius 3, then those circles, they do not overlap. So 2 adjacent circles, they might be tangent to each other, but there's no overlap there. So if we draw the circles, then it's like that. Okay, so it seems that we can have 5 more circles there, which means we're gonna have 5 more spheres. So we also need to pay attention to one extra thing. So it seems that right in the center here, we can also put a circle with radius 3 and centered around P. We're able to put a circle there, but in fact, we're not able to put the sphere right in the middle here because the height there is not enough. You see that for this sphere, it fits there because we have more room here than in the center. So right in the middle, we cannot fit another sphere in it. That's why the most number of spheres we can fit there is just 5, in addition to the one that's already there. So the answer is D. All right, so problem 21. 5 men line up to board a bus that has 5 available seats. Each man has a ticket with assigned seat. However, the first person to board has lost his ticket and forgets his seat number. So he takes a random seat. After that, each person takes the assigned seat if it's not occupied, and one of the unoccupied seats at random otherwise. What is the probability that the fourth person to board gets to sit in his assigned seat? So for this question, we can do casework based on what seat the first person is going to take. So the easiest case, the first person just takes seat number 1. So 5 seats there, and the first person takes the seat number 1. So let's put 1 on the first spot there. In that case, everything's good because the second person is just gonna take his own seat. So let's put 2 there. And then the third person is gonna take the seat number 3. And the fourth person will take the seat number 4. All right, so this is what we want, right? The fourth person takes his own assigned seat. So everything's good here. And the probability of that happening is 1/5. Because for the first person, the probability that he takes the first seat is 1/5. That's the first case. Second case, let's also look at an easy case there. So the first person might take the seat number 5. Let's take a look at that case. Okay, so then the second person is going to take the seat number 2 because it's not occupied. The third person is going to take the seat number 3. And then fourth person will take the seat number 4. So again, everything's good. So the probability of that is 1/5. That's just the probability that the first person is going to take the seat number 5. Okay, next case. Maybe the first person takes the seat number 4. That's also pretty straightforward because in this situation, the fourth person is never going to take seat number 4 because the first person is already there. That means the probability here is just 0. Right? The fourth person is never going to take his own seat. Okay, so I guess we have 2 more cases to go. The fourth case, maybe the first person can take the third seat, seat number 3. If that happens, then the second person will, of course, take the seat number 2. And now the third person's seat has been taken. So he needs to take a random seat. So 3 subcases. first case, the third person is going to take the seat number 1. That's good because the fourth person is going to take seat number 4, and that's what we want. Second subcase, the third person takes the seat number 4. That's terrible because the fourth person is never going to take his own seat. So it's not going to work here. And finally, the third subcase where the third person takes the seat number 5. Now the fourth person can take his own seat there. So that's good. So we see that the probability here is 1 over 5 times 2 over 3, 2/3. 1 over 5 there represents the probability that the first person takes the third seat, and this 2/3 represent the probability that, in this case, what's the probability that the fourth person is going to take his own seat. So the product here, and that's equal to 2 over 15. Okay, finally, last case, first person takes the second seat. Now for the second person, his seat has been taken. So now the second person needs to make a choice, right? He has to randomly take one of the remaining seats there. So we need to do subcase. The first subcase, second person takes the first seat. Then everything's okay because third person is going to take the seat number 3. Fourth person is going to take the seat number 4. So everything's good. Second subcase. So the second person might take the seat number 3. Now for the third person, his seat has been taken. So he needs to choose between the first seat there, the seat number 1, seat number 4, and seat number 5. That's actually quite similar to the case above there. So the probability of that happening is like 2/3. So 2/3 of the time, things are good. Okay, third case. The second person might take the seat number 4. And that's bad, right? Because the fourth person's seat has been taken. So it's not going to work. And finally, the last subcase there, where the second person takes the seat number 5. Everything's good because the third person is going to take the seat number 3, and the fourth person is going to take the seat number 4. So everything's good. All right, let's compute the probability. So 1 over 5 times, each of the subcase here is like 1 over 4. So 1 over 4 times, if things is good, then it's just 1 over 4. So here we need to multiply 1 over 4 by 2 over 3, by 2/3. And nothing's happening here. And here is another 1 over 4. All right, let's compute it. So it's 1 over 5 times 1/2 plus 1 over 6 So 1/2 plus 1/6, that's 2/3. 2/3 times 1/5, that's 2/15. All right, and now we have finished our casework. And the only thing we need to do is to take the sum of everything. We got 1/5 here, 1/5 here. We have a 2/15, 2/15. So let's take the sum. 1/5 plus 1/5 plus 2/15 plus 2/15. So that is 5 plus 5 plus 2 plus 2/15, which is 3 plus 3 plus 2 plus 2 over 15. So the top is equal to 10. So it's 10/15, which is 2/3. So the answer is 2/3, which is D. Problem 22. So we have A, B, C. There are real numbers that satisfy those three equations. We want to find the sum of all possible values of a squared plus b plus minus c. So those three equations, they're really similar to each other. So it's a good idea to take the difference and see what we can get. So we have the first equation, second equation, third equation. First, let's do 1 minus 2. So the right-hand side is, of course, 0, and the left-hand side is AB plus C plus 5, then minus BC plus A plus 5. So we have AB minus BC plus C minus A, that's equal to 0. So C minus A seems to be like a common factor of the first two terms and the second two terms. So we have C minus A times 1 minus B, and that's equal to 0. So two cases here, either B is equal to 1 or A is equal to C. So that's what we get from taking the difference of the first two equations, the equation 1 and the equation 2. And similarly, we can get some other information, for example, by looking at equation 2 and equation 3. We're probably going to get like A is equal to B or C is equal to 1. So let me write it down. If we do 2 minus 3, and by similar reasoning, we're going to get maybe C is equal to 1 or A is equal to B. By doing this 3 minus 1, we're going to get A is equal to 1 or B is equal to C. So now we can do some case work, I guess. So let's start with whether there's a number in ABC that is equal to 1. Because if there's not, then that just means all three numbers have to be equal to each other. So case work. First case, none of A, B, C is equal to 1. Then from what we got there, we have to have like A is equal to B is equal to C. Now the equation becomes A squared plus A minus 5 is equal to 0. But we can look at the discriminant here, and there's A squared plus A plus 5 is equal to 0. So now we can tell from the discriminant that there's no real solution. So discriminant is minus 1 squared minus 4 times 1 times 5. So that's clearly smaller than 0. So no real solution. Okay, that just means our first case doesn't work. So next case, so some of them, sum of A, B, C have to be equal to 1. Let's say if A is equal to 1, then what do we have? Well, if A is equal to 1, then our three equations become B plus C is equal to B plus C plus 5 is equal to 0. And also we have 1 plus BC plus 5, that's equal to 0. Okay, so simplify that a little bit. So we have B plus C is equal to minus 5, and BC is equal to minus 6. Okay, so then from Vieta's theorem, we know that B and C are the two roots of the quadratic equation x squared plus 5x minus 6 is equal to 0. And then we can factor this quadratic expression. So we have x plus 6 times x minus 1. That's equal to 0. So two roots are x equal to negative 6 or x equal to 1. So negative 6 and 1 are the two roots of this quadratic equation. So we have b is equal to negative 6, c is equal to 1, or b is equal to 1, c is equal to negative 6. Okay, so this is the case where a is equal to 1. So similarly, we can have another case where maybe b is equal to 1. Then everything is the same. We're going to get, a is equal to negative 6, c is equal to 1, or a is equal to 1, c is equal to negative 6. And similarly, the last case, when c is equal to 1, we're going to get a is equal to negative 6, b is equal to 1, or a is equal to 1, b is equal to negative 6. So now we can, it seems that there are only like 3 solutions to the equations. So the three solutions are a is equal to 1, b is equal to 1, c is equal to negative 6. And also the other two that are pretty similar, a is equal to 1, b is equal to negative 6, c is equal to 1. And the last one is a is equal to negative 6, b is equal to 1, c is equal to 1. Cool, now we've found all of the solutions. So we can compute the value of the expression, which is a squared plus b minus c. So a squared minus b plus c. So for the first case here, we have 1 minus 1 minus 6, which is negative 6. For a second solution here, it's 1 plus 6 plus 1, so it's 8. And the third solution, we have 36 minus 1 plus 1, so that's 36. Now we can just take the sum. Negative 6 plus 8 plus 36, so that's 38. So the solution, the answer is C here. Problem 23. This is a geometry question. We have ABCD, that's a cyclic quadrilateral, with AB is equal to 2, AD is equal to 4, CD is equal to 4, and BC equal to 6. And we want to find the length of BD. So assume AC and BD intersect at the point P. So there are actually two pairs of similar triangles in this graph. Since ABCD is a cyclic quadrilateral, we know that angle PBA is equal to angle PCD. And also angle PAB is equal to angle PDC. So the two right triangles there are similar to each other. So triangle PAB, that's similar to triangle PDC. Assume PA is equal to X. Then we know that this PA over PD is equal to AB over DC. But AB is equal to 2, CD is equal to 4, and then that's just 1/2. If PA is equal to X, then PD must be 2X. Okay, so by similar reasons, we also have another pair of similar triangles, PAD and triangle PBC. Again, it's because angle PAD is equal to angle PBC, and the angle PDA is equal to angle PCB. So the two green triangles there, they're also similar to each other. So triangle PAD, that's similar to triangle PBC. We have PA over PB. This is equal to PD over PC. PD over PC, and that's equal to AD over BC. But we know AD is equal to 4, BC is equal to 6, so that's 4 over 6, which is 2 over 3. Since we know PA is equal to X, then PB should be equal to 3/2 times X. So PB is equal to 3/2 times X. And we also know that PD is 2X. That means PC must be equal to 3X. Okay, so PD is 2X, PA is X, PB is 3/2 times X, and PC is equal to 3X. All right, so now is the perfect time to use the Ptolemy Theorem. Here's the brief review of the Ptolemy Theorem. Ptolemy Theorem. So we know that if we have a cyclic quadrilateral ABCD, cyclic, then we have a nice relationship among the size of the quadrilateral here and also the two diagonals, which is this AC times BD, the product of the length of the two diagonals, that's equal to AD times BC plus AC times BD. AD times BC
plus AB times CD. So that's the sum, the product of the opposite two sides. And then since there are two pairs, it's one pair, two pairs, and we take the sum. So that's the right-hand side. And now this is a perfect time to use the Ptolemy theorem, because we also have a cyclic quadrilateral here, and we know, basically we know everything in terms of those constants and also those x's. So in this question, we have AC times BD, that's equal to 4x times 7/2 x. AD times BC plus AB times CD, that's equal to 4 times 6 plus 2 times 4, which is equal to 32. Okay, now we have the equation. So 14x squared, that's equal to 32. So x is equal to 16/7. Now we can compute the length of BD. So BD is 7/2 times x. Sorry, so we need to take the square root of 16/7. So x squared is equal to 16/7. So that means x is equal to 4√7/7. So BD is equal to 7/2 times x, and that's equal to 4√7/7 times 7/2, and that is equal to 2 times √7. And the answer is B.
All right, problem 24. So first, let's think about how we can make a number whose remainders on division by 4, 9, and 25 sum up to 17. Well, the easiest way is that first we pick its remainder on division by 4. So mod 4, let's say the remainder is A. And then we pick its remainder on division by 9. Mod 9, and let's say the remainder is B. And then for mod 25, we need to do 17 minus A minus B. So here we got 4 choices for A, right? A could be 0, 1, 2, 3. And there are 9 choices for B. B could be 0, 1, 2, 3, and all the way through 8. And then after we fix A and B, the numbers remainder on division by 25 is fixed. It should be 17 minus A minus B, because we want the sum of 3 numbers to be exactly 17. Okay, so seems that we have 36 numbers that satisfy our condition. So we can just pick a number here for A, pick a number here for B. Then we also have 17 minus A minus B. Okay, so with those 3 remainders, do we have a 3-digit number that corresponds to those 3 remainders? The answer is yes. So first of all, with the remainders of mod 4, mod 9, and mod 25, from the Chinese remainder theorem, we know that the 3 remainders there will uniquely determine the remainder of that number mod 900, which is 4 times 9 times 5 times 25. So that's mod 900. Okay, as long as we have the three remainders there, we're going to have the remainder of that number mod 900. But then we also know that if we know the number's remainder on division by 900, then actually that uniquely determines a 3-digit number, because we have exactly 900 3-digit numbers. And those 900 3-digit numbers, they're just all of the residual classes modulo 900. Okay, so now we see that each of our choice here, and in total that there are 36. So each choice here corresponds to one 3-digit number. And now we want to find the sum of all of those numbers and essentially just the remainder of that sum on division by 900. So we're going to do it in like 3 steps. So first of all, let's denote the sum by S. We want to find the remainder of S on division by 4. So S mod 4. Okay, so we know that there are 36 terms in S, and we see that 9 numbers there, they have remainder 0 on division by 4, and 9 numbers there, they have remainder 1 on division by 4, and similarly there are 9 numbers whose remainder is equal to 2 on division by 4, and 9 numbers whose remainder is 3 on division by 4. So that means S is congruent to 9 times 0 plus 1 plus 2 plus 3, because those are their remainders on division by 4. So that is congruent to 2 mod 4. So here's 6 times 9, 54. So that's congruent to 2. And similarly, we can find the remainder of S on division by 9. So we have 4 zeros, 4 ones, 4 twos, and all the way to 4 eights. So and so here we can just pair everything up, right? We have 1 8 2 7 3 6 5 4, and here's 0. So this thing is divisible by 9. So that's congruent to 0 mod 9. And finally, we need to find the remainder of S on division by 25. Okay, so what are the remainders of those numbers mod 25? Well, they are just 17 minus A minus B, with A being one of the 0, 1, 2, 3, and B being one of the 0 through 8. So the sum is congruent to, so first of all, we have 17 times 36, because there are 36 numbers, and each of them has a 17 in the front. Then we have this minus A minus B, and when we take the sum, that's going to be 4 times 0 plus 1 plus 2 plus dot 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 all the way through 8, and then minus 9 times 0 plus 1 plus 2 plus 3. You know, just the same as the previous 2 cases there. Okay, then just some computation going on. So we have, we only care about mod 25. So we can simplify this a little bit. This 36 simply becomes 11. So 17 times 11 minus 0 plus 1 plus dot 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 plus 8. That's equal to 36. So again, 36 is just 11. So that's minus 4 times 11 minus, we have 6 times 9, that's 54. But 54 is simply 4. in terms of mod 25. So minus 4 there. Okay, what is that? We have 17 times 11 minus 4 times 11, so that's 13 times 11, which is 143, and minus 4 there. So the last two digits here are 39, and that's equivalent to 14 mod 25. Okay, we're almost there. There's just one last step. So now we have the remainder of S on division by 4, 9, and 25. So S is equivalent to 2 mod 4. S is equivalent to 0 mod 9. And S is equivalent to 14 mod 25. Okay, so with this information, we should be able to find the remainder of S on division by 900, again, from the Chinese remainder theorem. So I guess we can start with the third equation here. We know we can write S as 14 plus a multiple of 25. So K is the integer here. At the same time, we want S to satisfy the first equation. S is equivalent to 2 mod 4. And we can simply try some numbers of K. So apparently when K is equal to 0, that works. So when K is equal to 0, we have S equivalent to 2 mod 4. That means the number 14, when K is equal to 0, the number 14 satisfies both the first linear congruence equation and the third congruence equation. So we have we can write as as 14 plus a multiple of 100. So this 100 is simply 4 times 25. Because 14 satisfies the first equation and the third equation. And you want to keep those two equations satisfied. So the way to do it is to add some multiples of 100 to your 14. And then you just want your number here to satisfy the second linear congruence equation. So you want this number to be a multiple of 9. We know this 14 has a remainder of 5 mod 9. So what we need here is a 4 mod 9. But 100 is equivalent to 1 mod 9. So that's why we need to take this K1 to be equal to 4. So K1 is equal to 4 to have S is equivalent to 0 mod 9. All right, if K1 is equal to 4, then of course this S is equal to 414. Mod 900. Okay, so the answer here is 414, so that's D. Okay, problem 25. So this is a counting question. There are 10 cards. Each card has 2 different numbers from 1, 2, 3, 4, 5 on it. So let's say that the 10 cards are well, let's just do this 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, and 4, 5. So each of them is like a 1 card. There are 10 cards in total. No 2 cards have the same 2 numbers on it, okay? put these 10 cards into 5 boxes labeled 1, 2, 3, 4, 5. So 5 boxes there labeled 1, 2, 3, 4, 5. A card with numbers I and J on it can only be put in either box I or box J. So for example, the card 3, 4 can only be put into the 3rd box or the 4th box because the card has the number 3 and 4 on it. Let n be the number of ways we can place these 10 cards so that box 1 has more cards than any other box. What's the sum of digits of n? Okay, so the critical condition here is the box 1 has more cards than any other box. So let's do casework based on the number of cards in box 1. First case. The best case for us is definitely like all of the cards with 1 are in box 1. So box 1 has all of those 1, 2, 1, 3, 1, 4, and 1, 5. Everything's there. Okay, now there are 4 cards in box 1. And if you look at the other numbers, for example, number 2, we see that there are only 3 cards with number 2 on it left, which are 2, 3, 3, 4, and 3, 5. So even if we put all of them in box 2, then our condition is still satisfied. Like box 1 still has more cards than any other box. So now we can actually freely place those 6 cards left in those 4 boxes. Well, apparently we need to follow the rule that that for the card IJ, it should be put in either box I or box J. So 2 choices for any of the 6 cards left. So the number of ways is simply 2 to the number of 6. So that is 64. All right, so we're done with our first case. Second case. For second case, we're going to have 3 cards in box 1. So of course, the first question is like which 3 cards, right? We have 4 cards with 1 on it. So we need to choose 3 to put into box 1. So things are pretty symmetric. So let's assume that we put 1, 2, 1, 3, 1, 4 in box 1. And then we have like 1, 5. We have the card 1, 5 left. So we can only put that card into the last box, 1, 5. We need to remember that after figuring out the number of ways here, we need to multiply this by 4 because there are actually 4 ways to choose 3 cards from 4 to put in box 1. So let's put a 4 there just to remind us that we need to multiply the number of cases by 4. Okay, so now what should we do? We know 1, 2, 1, 3, 1, 4 are in box 1. We know 1, 5 is in the last box. And we also know that for each of the 4 boxes there, they can contain only at most 2 cards. So since there's already 1 card in box 5, let's do some more casework based on the number of cards in the last box. So first, a subcase. The first subcase is, so the card 1, 5 is the only card in the last box. So that means we cannot put 2, 5 there, we cannot put 3, 5, or 4, 5 there. So the 2, 5 should be placed in the second box, 3, 5 should be placed in the third box, and the 4, 5 should be put in the fourth box. Now we have 3 cards left, 2, 3, 2, 4, and 3, 4. So if we think about it, then there are actually only 2 ways to place those 3 cards there, because for example, you can put 2, 3 in the second box. Then the card 2, 4 can only be put into the fourth box because there are already 2 cards in the second box. So you must put 2, 4 there. And then you look at the card 3, 4. 3, 4 can only be placed in the third box because the fourth box there are already 2 cards. So we can do 2, 3 here, 3, 4 here, 2, 4 here. That's one case. Let me write it down there. So I'm gonna copy everything. So we have 2, 3 in the second box. Then we know that this 2, 4 cannot be put here. So the only place for 2, 4 is the fourth box. And then we have the card 3, 4 left. That can only be placed in the third box. That's one subcase, and there's another one. So here, we can put 2, 3 into the third box. And then the card 3, 4 cannot be put here. So it can only go to the fourth box. And then we can put 2, 4 only in the second box. All right, so we have those 2 cases. That's the first subcase. When that's first subcase where 1, 5 is the only card in the last box. Second subcase. We have 2 cards in the last box. So 1, 5 is already there. We need to pick one from 2, 5, 3, 5, and 4, 5. So again, things are pretty symmetric. So we can assume that 1, 5 is there, and also 2, 5 is there. Let's write number 3 there to remind us that we need to multiply the number of cases by 3. Because there are 3 ways to choose card here. Could be 2, 5, could be 3, 5, could be 4, 5. Okay, now the 3, 5 should be in the third box, and 4, 5 should be in the fourth box. Okay, again, we're left with 2, 3, 3, 4, and 2, 4. Let's do casework again. So let's see. Where should this 2, 3 go? Well, we could put 2, 3 in the second box. Let's try that. Now we have 3, 4, and 2, 4 left. Seems that everything's good here. The only way for it to go wrong is that we put 3, 4, and 2, 4, put both of them into the fourth box. That's the only case where things can go wrong. Otherwise, everything's good. In each box, there are at most 2 cards. So basically, we can put 3, 4, and 2, 4 freely, except for one case. So the number of valid cases here is 2 times 2 minus 1. Because 2 choices for 3, 4, 2 choices for 2, 4, and the only case that can go wrong is we put both 3, 4, and 2, 4 into the fourth box. So 3 cases there. Next, if we do not put 2, 3 in the second box, we need to put it in the third box. 2, 3. Remember, we have 3, 4 in the second box. Sorry, we have this 3, 5 in the second box. Now we also put 2, 3 there. So that means for the card 3, 4, we cannot put it in the third box. So we need to put 3, 4 in the fourth box. But then we see that in the fourth box, there are 3, 4, and 4, 5. 32 cards. So for the card 2, 4, it cannot be put there. So 2, 4 can only go to second box. So clearly, there's only one case like that. Cool. Seems that we're done. And we just need to sum up everything, all of the cases here. So first of all, we have 64. Let's have 64 here. And then in our second case, remember here's a multiplier of 4. So it's 4 times something. So what is that something? The first subcase, the number of cases is 2. So here's 1, here's 2. So 2 cases there. And for the second subcase, we have 4 cases here. But remember, we need to multiply that by 3. So 4 times 3. Okay, so that's 64 plus 4 times 14, and that's 120. We're going to find the sum of digits for this number. So the sum of digits is equal to 3, and that is A.